file, I couldn't have do it. So let's start. So before we start, we are going to release we are actually going to release the assignment 1 specifications today. So it's actually ready, and you will be submitting through the GIF on WebCMS. And I believe you have used it before, right? So so you will have no, but it's relatively easy to use. You can ask a friend how to use it, and the deadline for this assignment 1 is the end of next week by this Sunday's 10 p.m. So let's start. Oh, there's some problem with it. Oh, it has gestures. Okay. So so today's topic is about structural testing. So in our last week, we have learned functional testing or black box testing. So as you can expect, we are going to learn white box testing today. So before we jump into the actual topic of what is structural testing, let's consider this dilemma for every software company. So first, if customers experience no bugs, so why do we need to do testing or quality assurance? So if the customer cannot experience bugs, why do we need to do this? It's quite costly to maintain a testing team to do these testings. However, if customers do find bugs when they use the product, it is often too late to do testing or quality assurance. So this is the dilemma here. So as a tester or developer, what we have to answer is, are the tests good, or are the tests good enough so that we can stop writing new test cases? So we need to somehow measure the adequacy of testing. So we want to show that we have done certain level of testing. And ideally, what we want to do with testing is that we want to find all the bugs. But the software will simply tell you this is impossible. It's impossible for us to find all the bugs in a very complex software, especially the real-world ones. And in reality, what we usually get in the end is either we compiled the code and it worked, so it means that we simply do no testing, or we run out of budget, so we can't finish our testing plan. We can't do comprehensive testing. And this actually will leave the testing task to the customers, and this is not what we want. And this is inadequate. So you can see what we want, the ideal case, is impossible. But most of the time, if we don't have a very good design, we will get inadequate tests. So a good measurement of testing adequacy should compromise between impossible and inadequate. And we need, in order to measure the adequacy, we need to come up with some metrics. So this metric is, so normally test adequacy metrics helps us to score testing efforts by measuring the completion of a set of test obligations. So this is more like a I think there's some problem with a mic here. I don't know if it is recorded or not. It's not recorded, right? You can't hear the mic? You can't? Uh, I think it's working. Yeah. Let me check the volume. It's very high. Maybe let me try the handheld mic. Hello. I think it might be the issue of the audio system here. So should I turn this one off? Hello. Not better, I think. Maybe. Is it better? Slightly better. Yeah, okay, let's use this one. And this one is the best one we can get today. I think there's some problem with the classroom today, and there's no icon here, right? And the icon is not working as well. Actually, we are the customers. We shouldn't test it. And we are the best QA tester for this classroom. And okay, but anyway, let's stick with what we have for now. And in order to, sounds better now, right? So in order to in order to show that we have done enough testing, we need to use some kind of metrics to show our effort to our customers or to whoever is interested in this software. So from a personal point of view, this is somehow like what we do for blockchain. Is like a proof of effort. So what we need to do is we can never show our customer that our software is free from bugs, but what we can show them is that we have done enough of testing. We have done a very comprehensive testing, and we need some proper metrics. And let's try to find out these proper metrics step by step. So first, let's start with the ideal case. The ideal case is that we want to find all the bugs, but we know that it is impossible. So can we approximate this? Can we do an approximation of finding all the bugs? So the idea here is if a test case cannot reach or cannot exercise a statement, then we can never find the bug in that statement, right? If the requirement specifies, let's say, 2 outcomes of a function, and we can only exercise or we can only get one of the outcomes, then we can never verify the bugs with the other outcome, right? So what we want is we want to show some coverage of these statements or requirements. So we want to show them, we want to measure what we have already covered. So if we cannot cover a statement, if we cannot cover a specification requirement, then we can never find that bug. So what we need here is coverage. So what we want to have now is some adequate metric that is related to faults in software. And this adequacy metric is actually widely used in industry. It's easy to understand, and it could be easy to automate. And normally it offers a checklist, and you will encounter some of the measurements of code coverage, some measuring tools, actual tools in assignment tool. But for this class, we are not dealing with actual or concrete tools. We are dealing with some concepts. So let's continue. And some of the metrics could be derived from the requirement specifications, but the majority of the metrics are coming actually from the source code of the target program. And so that leads to structural testing. So structural testing is to derive test cases from the program structure directed by a chosen adequacy metric which is related to the coverage of something. And you may wonder, okay, why it is called structural testing? But now you know why it is called structural testing. The structural here refers to the structure of the program under test. So now let's come to our second topic today, structural testing. So there are some common structural coverage metrics. So for example, we have statement coverage, we have branch coverage, condition coverage, we have path coverage. And the idea here is that the structure of the program itself gives us a lot of information for testing. And because we know what's happening inside the program, what's happening inside the target program, so it is called white box testing in comparison to black box testing. So what we do is what we care about most here for structural testing is that we want to find a family of metrics that could be used to define how and which code has been executed. And the goal is to exercise a certain percentage of the code. Why it is only a certain percentage here? Can we achieve full coverage? You can leave this question to our next lecture. We will show you why we cannot achieve full coverage. But the basic idea is we can't find all the faults without exercising all the code. And the key here is how do we define all here? So we have different metrics for measuring coverage, and that is what interests us most here. And the motivation of having structural testing is that requirement-based tests are not enough. Most of the time, they could execute a lot of code, but they are not directly related to the actual code. So they rarely execute enough code coverage. For example, here are some cases where black box testing may not do well. So for example, in some programs, we could have some helper functions which are not directly related to the specifications. So they are just some utilities, some utils. So for these functions, because they are not specified in the requirements, we can't effectively test them using black box testing. Okay. Yes, yes. And that is actually what we will cover in our next slide, the workflow of structural testing. But here, you just now you mentioned some keywords like the structures of programs. So, but programs could have different types of structures, right? What kind of structure do we care here? And we will learn that later today. So, the second type of code that black box testing may face difficulty dealing with are those error handling code. So they could cause some problems because of the lack of specifications, and of course there are some program outputs which are missed in the requirements, which could not be described in the requirements. For example, in our last lecture, we have tried Radamsa, a random black box fuzzer, try to use it to test a simple C program. And in that simple C program, there is an out-of-bound read problem when we try to read a file into a buffer. And that buffer size couldn't be a proper specification. And that's why we sometimes the requirements may not be comprehensive enough to describe every detail in the actual code implementation. So that's why we need to test the code. And the structural testing actually complements black box testing. So functional testings are actually good at exposing conceptual faults because they are directly related to the high-level requirement specifications. And structural tests are good at exposing actual coding issues. So let's come back to some theory crafting. So in our second lecture, oh, there are some special gestures with this internal laptop. But anyway, so in our second lecture, we have learned that there are 6 testing principles. So we know that in black box testing, we care the most about partitioning because we want to partition the input space. So which one of the principle is mostly used for white box testing here, according to what we have learned just now? So these concepts are not just we learned it and we throw it away, but we try to come back to these principles from time to time. So which principle is mostly used here? And actually visibility and observability, because just now I mentioned that partition is for black box testing. And because we want to partition the input space. So why visibility and observability is important here? Because we want to measure, we want to observe from the program. We want to observe the coverage, the metrics from the program. So that's why we need visibility and observability. We are mostly interested in different measurements of coverage here in this white box testing. So, like I mentioned, let's try to discuss structural testing workflow. Is someone coming in? Okay, good. So, for structural testing, we are learning structural testing today, white box testing. Okay, so for structural testing, what we normally do is we try to take the code, derive information about the structure, and use the test obligation information to derive test cases to measure the adequacy of existing test cases. So we measure the coverage, whatever coverage of the tests we have derived. And we do it iteratively so that we can continue to refine our test cases once we have collected more information during testing with our existing test inputs. So we iteratively improve the entire test suite once we have found more and more about the program structures. So this is normally what we do for structural testing. And before we jump into different details or different adequacy metrics, let's try to answer the question, what kind of program structures do we want to cover? What kind of program structures? So first, almost all the programs we are using today are made up of statements. And there are some definitions, some more formal definition of statements, but that's not the core interest of this course. So there are different types of statements. For example, there are some simple statements. We could have assignments, but this assignment is not the assignment you do, but it's like more like value assignments. So we assign values, and that is one type of statement. And we could have call to functions, we could have assertions, we could have go-tos, which are just jump, and we could also have some returns as simple statements. And we could also have some compound statements like the counter statement loop. So the counter statement loop is actually just for loop. And we could have while loops, we could have if statements, we could have else, we could have cases and switches. We could also have exceptions. So statement is one of the basic building blocks for our modern programs. And we can use statement as one of the program structure here to use. And the second types of statements are, the second type of program structures are related to how the programs are executed. So this is important because we are doing testing. We need to run the program. So we need to have context on how the system executes. And most of the time, code is rarely sequential, so it's not all the way down from the input to the output. It has branches. So there are some conditional statements that will result in branches during execution, jumping from different blocks of code. And control flow is used to describe how this control is taken over from code block to another code block. So you can think of control as because in the early days, programs were not stored in some binary in our hard disks. They are like tapes. So there's a head reading the tape, a magnetic head reading the tape, and you can think of the control as how we move the magnetic head of reading the code. And in modern computers, of course, you can think of it as how the CPU processes different instructions. So control flow is more about caring about the logic of how we execute different branches for a program. And for example, for this simple C program, we could have multiple branches when we execute because we have the while here, we have the if and else there. So when we execute this program, it's not running statement by statement. It's actually running according to these control flow restrictions. And another thing here, another important concept is called data flow. Data flow is how information of different variables are used in some other expressions. So, but in this course, we are more concerned about control flow because there's another course covering data flow analysis, and that course is 6323. And that course is a mixture of undergraduate and postgraduate. So that in that course you will be learning about data flow analysis. But in this course, we will mainly discuss control flow analysis, and we will cover a little bit of data flow analysis. So as I said, we are more interested in control flow graphs. And control flow graph is actually a directed graph representing the flow of control through the entire program. And it is a directed graph. It means that the edges have directions. So it means how the control is passed from one block to another. And each one of the node represents a sequential blocks of program statements. So that means that the statements inside one basic block or one node here in the control flow graph, they will always execute together. So if we execute, for example, for the first basic block, if we execute the val here, we will always execute the second statement here. So that's why we put them into one basic block or one node in this control flow graph. And edges are connected. So edges connect the nodes in the sequence they are executed, as I just mentioned, because this is a directed graph. The direction of the edges means the execution sequence. And multiple edges coming out of a single node means there are branches. So for example, we have a branch here in this. Let me see if I can use some advanced features here, since we are using this internal computer. So as you can see, we have branches. We have a branch here because two edges are coming from basic block 1. We have a branch here because two edges are coming from basic block 2. And like I just mentioned, a basic block is not simply one statement. A basic block could be a sequence of statements where there's no branches in between the basic these sequences. And one other thing you would also like to notice here is that we have an exit block for this program, because normally for control flow graph we should have entry and exit nodes, but in this example here we don't really need an entry node, because the entry node is just simply basic block 1, but we have to add an exit block to make it more complete, so we can indicate when the program will terminate. Because if we don't have this exit node here, we don't know when the program will terminate, right? So you know that we need this exit basic block. And if you wonder how this control flow graph is rendered or is described, you can this is actually a dot file, and you will be using it for your assignment 1. So this is the actual source code to generate this control flow graph. So that's the control flow graph. And for coming back from the structures, different structures, to the coverage criteria, we should have so we can derive different coverage criteria from control flow graphs. So for example, we can have statement coverage. So in statement coverage, we care about the nodes of the control flow graph. We could have branch coverage, where we care about some edges of the control flow graph. We could also have condition coverage. We could also have path, and many more coverage criteria. So as you can see, we could care about the basic statements, and we also care about these branches coverage. So now let's come to the first coverage we will be learning today, statement coverage. So statement coverage is actually the most intuitive criteria here. We just count how many statements we have covered. And what we want to achieve is to execute every statement in the program with our test suite. And that means we have to cover each node of the control flow graph. And the idea here is that the basic idea is we can never find a bug of a statement if we never exercise that statement. And the coverage is described as the number of covered statements divided by the number of total statements. That is quite straightforward. And let's do the second level today. So how many nodes are there? Based on what you have learned with the control flow graph example, how many nodes are there in the control flow graph for this program? So can you quickly count? And let's ignore the entry node. So how many nodes are there? Should we have? We got one. Actually, we should have 6 nodes, and we have one correct answer here. I don't know who is doing that, but okay, Kongbin is doing that. So we actually have 6 nodes, because although we don't consider the entry node, we should consider the exit node to indicate when the program ends. So what we have is for each one of the for each statement, we can have one basic block. In this case, for each statement, we have one basic block, and we have one other basic block as exit. So this is what we get for statement for the basic block for the control flow graph of this program. And let's continue. So how many test cases do you think we need to cover all the nodes here? How many test cases do we need to cover all the nodes? This is actually quite tricky. You have to be careful. How many? Yeah. Oh, you saw the answer from the slides. But since you have since I have seen the answer, do you know why? Not really, because we have to cover all the nodes, right? We have to somehow cover everything here. So you may think that, okay, we need one to cover this. We need one to cover this. But that's not true, because let me tell you the answer first. We only need one test case to cover all the statements in this program, in this small, simple program. That is because of the loop here. We have a loop. So this simple small program is trying to flip the value of some negative values of a given array or given list. And the number of values to be flipped is decided by this variable n here, by this n here, and because we can control how many elements do we have and the content of the elements of the list, what we can do is we can try to use one single test case to go through everything here through the loop. We can use one single test case, imagine, to go through all the loops, to go through all the nodes here. So that's why we only need one test case. So can you come up with a test case, an example test case to do this? Can you come up with an example test case to do this? This is not on the slide. We can do it here right now. So this program takes 3 different parameters: a list and a limit n and integer x. So x is like a termination for the loop. So what we can do is, first, while I is smaller than n and ai is smaller than x, so what we can have is, let's say n equals to 2 and x equals to 3. We can just assign some random values to fulfill this condition here, to make it true first. And for example, ai, because I starts with 0 in the first iteration, so let's say the first item here is 1, and this will allow us to go through the true branch here. And if AI is smaller than 0, we go this branch. So we make it a -1. Then we will go through this true branch here. And we will flip it and I++. And then we go back to the while loop again. We go back to the while loop again. And let's try to make the test case simple. Let's try to terminate the program here. So this time we can make sure that one of the conditions should not be satisfied, but we can't really do it with only one element. We have to do it with 2 elements because I++. So what we can do is we can set the second element to be 4. This time A1 is bigger than X. This condition is not fulfilled. We will go through the false branch here. So in this case, this single test case can help us to cover all the statements of this program. So this is roughly the workflow of doing white box testing. We have to, we can't get to the correct answer by just taking a look at the program. We may have to follow the control flow, follow the execution. We can do some assumptions. We can get back to refine our test cases once we have collected more information from the program. So this is why the workflow is a two-way workflow. It means that we need to generate test cases to test the target program, and we need to collect information from the target program to refine our test cases. So let's continue. So what kind of faults could we make if we only do statement testing? Actually, we may miss some edges. In the test case we have just generated, we can cover all these edges, all the edges I have painted here, but we have missed one edge here. That is the false for AI smaller than 0. So what if the condition here is somehow implemented wrongly? Let's say somehow the programmer made a typo, implemented as AI smaller than 1. Then we cannot detect this error here with the test case we have just generated because we have missed a branch. We have missed an edge here. So that's why with statement coverage, sometimes we may miss out some faults or some bugs, even if we cover all the statements of a program. And let's have a 10 minutes break, and I'll see you at 3 o'clock. Okay, let's start our second half of lecture. Although I think it's better if we wait for the last 15% of our class today, because we have 15% of students missing for the second half. We should wait for that for the 15% of students. But all right. But anyway, let's start. I think if we can start earlier, we can have some time to discuss the assignment 1 today. So let's continue the coverage criteria. So the next coverage we are interested in. Oh, it's not displayed. Okay, we have now everyone here. So okay, let's continue. So just now we have discussed the concept of structural testing, the different types of program structures we are interested in, and we just discussed in detail about the control flow graphs and statement coverage. Now let's move on to another type of coverage, which is called branch coverage. And we have seen that statement coverage could miss some bugs. So we need a more comprehensive representation of code coverage. And let's come to branch coverage. So in branch coverage, what we want to know is, do we have test cases or do we have test suites that take all of the control branch at some point? So can we cover all the control branches with our test suite? And that is actually equivalent to covering every edge of the control flow graph. And this actually helps us to identify faults in some decision statements or those branching statements, if else loops. And the coverage of branch coverage is calculated as the number of branches covered divided by the number of total branches. And before we learn what is actually, how do we actually calculate, how do we actually use branch coverage, how do we actually count branches from the control flow graph, let's learn a concept called subsumptions, because we are now learning more than one types of coverage. So we need to somehow know the relations between different types of coverage criteria. So let's learn this subsumption concept. And subsumption concept is used to describe relations between different coverage criteria. And a coverage metric A subsumes another metric B if for every program P, for every test suite used to test the program, the test suite satisfying A, which is subsumed by B, which subsumes B, will also satisfy B with respect to P. So that means if we use the that is more like the include or inclusion relation in the concept of sets. So the A subsumes B means that A includes B. So if we satisfy A, then we don't need to satisfy B anymore, because A is considered stronger here. So what we can say is branch coverage actually subsumes statement coverage. It covers, actually, in order to cover all the edges in a control flow graph, we have to cover all the nodes. So that's why branch coverage subsumes statement coverage. But here comes the question, should we always use the stronger metric? Actually, we shouldn't. Actually, we have faced similar problems when we do black box testing. We have stronger testing designing, test case designing strategies. We have weaker ones, but we don't always use the stronger ones because we have budgets, because we have to fulfill some time or manpower budget. And if we use the more complex or more comprehensive metrics, we will end up having more test cases, which is not always useful in practice. So that's why we still need statement coverage, even if we could do branch coverage. So let's show how do we use branch coverage with an example here. So let's consider the same function we have used for statement coverage. So how many test cases do we need to cover all the edges? Don't look at the slides. Don't look at the slides. So how many test cases? 1. Okay, I hope it's not from the slides. And yes, I see from your gesture you are doing the correct thing. So this the answer here is still 1, and that's because what we can do is we can cover the branch like this. Once we finish the first iteration of the loop, instead of going to the false branch, we go to the true branch again, and then we go through the false and false here. So this is why we can cover every edge in this program with just 1 test case. And I won't go through the how do we find a suitable test case here. You can do it on your own as a practice. So we still only need 1 test case to cover all the edges. But this time what is difference is that we are covering this edge here. So we didn't miss this edge. And this program is actually quite special because it has a loop wrapping up everything. So we can use a simple long enough test case to cover all the statements and edges. What if we change this program a bit? What if we change the while loop, the while statement into an if statement? And then in this case, we need to remove this edge as well. We need to remove this one from the control flow graph. And this one will become another exit. So how many? Okay, good. You are answering before I'm asking. So we need 3 test cases to cover all the edges if we change the branch condition from while to if. We need 3 different test cases here. So just now, what you have seen with the original program is really a special case where a big loop wraps up everything. And you may notice that we need to deal with loops carefully. And we will learn that later in this week. And that's all about branch coverage. Let's come to condition coverage. So before we come into the actual coverage metric, let's first consider what is a decision and what is a condition. A decision is actually a complex Boolean expression. So it is often used for control flow branching. For example, we can use decisions in loops. We can use decisions in if and else statements. However, it is not always used in control flow branching. For example, we may assign some Boolean expressions to some variables. So decisions could appear either related to control flow branching or not. And decisions are made up of conditions which are connected by Boolean operators like AND or XOR or NOT. And these are the relation between decision and condition is that conditions makes up decisions. So this is the relation here. So a condition, you can consider a condition as a simple Boolean variable or sub expression that has only that could be evaluated to true and false with only one comparison parameter, one comparison operator. So that this is a condition, and if we connect conditions with Boolean operators, then we can get decisions. So this is the relation here. So if we do this, we get conditions. If we do this, we get decisions. So let's continue. So as you can see, we have different decisions, we have different conditions. So we can have decision coverage. Of course, we can also have condition coverage. And let's first deal with decision coverage. So branch coverage actually deals with only a subset of decisions. So as we just mentioned, decisions could appear in those branching conditions. It could also appear somewhere else, like in the variable assignments. So branching decisions actually is only a part of all the decisions we have in a program, and branch coverage is actually a subset of dealing with a subset of decisions. And decision coverage requires all the Boolean decisions evaluate to true and false. So decision coverage actually subsumes branch coverage. And of course, the coverage is calculated as the things we have covered divided by the total number of decisions. And now let's come to condition coverage. For condition coverage, we have a little bit more variations. We have the basic version of condition coverage, which is called basic condition coverage. And there are several metrics that, as I just mentioned, there are several metrics that examine individual conditions that make up a decision. And these are used to identify faults in those if and else or while statements. So the most basic form of the basic condition coverage is to make sure that every condition can take the value of true and false at least once. And the coverage is calculated like this. And let's come to a more concrete, a more detailed example here. So assume we have two conditions, A and B, and the decision is known as A and B. And can you imagine what will the decision, what will the basic conditions look like, different combinations of conditions look like to achieve full basic condition coverage? So we just simply need to make sure that both A and B can take the value true and false at least once with our test suite. So in this case, if we design the test cases for this decision to achieve full basic condition coverage, what we can do is we can have true and false, we can have false and true. So A takes the value of both true and false, B takes the value of both true and false as well. Of course, we can also have true and false. This will also lead us to 100% of basic block condition, basic condition coverage. But as you can see, this is very, very basic, because we can, in this example here, we can satisfy the branch without hitting both branches, because with both test cases, the value of the decision is always false. So we are not exhaustively testing the different situations for this decision here. So that's why this is called basic. So it's very incomplete. And we have a more advanced version of condition coverage, and that is called compound condition coverage. So it actually evaluates every permutation or every combination of the conditions, the true false values of conditions. Again, let's assume we have two conditions, A, B, and the decision is A and B. So can you imagine how many test cases do we need here? We actually need 2 to the power of 2 test cases. So the first 2 is that because every value can take true and false. The second 2 is because we have 2 conditions. So we need 2 to the power of 2. That is 4 test cases to cover all the combinations here for this decision. And compound condition coverage can subsume branch coverage because all the outcomes, because the number of test cases is more than enough to achieve 100% of branch coverage. So it subsumes branch coverage. However, it can be expensive in practice because for a decision with n conditions, we need 2 to the power of n test cases to cover all the combinations here. However, in reality, when we do testing, when we are given a specific programming language, we may do a short circuit evaluation, and this is somehow a programming technique when you try to develop some high performance programs. So in many programs, actually if the first condition could determine the result of the entire decision, and that is actually related to some logic calculation or logic operations. So for example, assume we have these 2 conditions, A, B, and the decision A and B. In some programming languages, if A is evaluated as false, then the program won't check the value of B. So the value of B is not checked yet. So in some programs, we could, if you put some calculations like A plus B here, then this is not calculated as If you put a function call in B that will return you a Boolean value, then the function call at the position of B is not executed. This is true for most of the programming languages you may encounter nowadays. For example, for Python, for C, for Java, all of them, if you have A and B here, and A is already false, then B is never evaluated. So this can help us to save some of the test cases here. So we can do a short circuit evaluation. We can take a shortcut. Instead of trying out both true and false for B, we can ignore the value of B and just set A to be false here. So we can save 1 test case in this case. And the last coverage criteria we evaluate today is called modified condition decision coverage, or MCDC. So it considers both condition coverage and decision coverage. So if we want to do if we want to have a comprehensive test suite to achieve full MCDC, so it requires all of the following conditions to be true. So the first one is each entry and exit point is invoked in the entire program. But here, since we are dealing with only one function, so we can ignore this. So the second requirement here is each decision takes every possible outcome values. Each decision must take every possible outcome value. The third one is each condition in a decision takes every possible outcome. The first one is each condition in a decision is shown to be able to independently affect the outcome of the decision. So let's come with an example here. So let's reuse the example of A and B. So this is actually the truth table for the conditions and the decision here. So let's see why it satisfies the 4 requirements of MCDC. So first, each entry and exit point is invoked. We don't need to care about this in this case. And second, each decision takes every possible outcome. And this is also quite clear because we can see that A can take the value of both true and false. B can also take the value of both true and false. And we only, each decision. So A and B is taking both true and false. So we only have one decision here. So we only need to care about this. So the second one requirement is also satisfied. The third requirement is each condition in the decision takes every possible value. We can see this is also satisfied because A takes the value of both true and false, B takes the value of both true and false. So the third requirement is also satisfied. And the last requirement is also satisfied. And let's see why. Because we can see when A is true, the entire condition is true, and when A is false, the final decision is false. So we can see that A independently is affecting the result. We can show this in this table. And what we can also do, what we also need to do is we also need to show that B could also independently affect the outcome of the decision. So we can see when B is true, the entire decision is true. We can also see when B is false, the entire decision is false. As you can see, in order to satisfy all these 3 conditions, we only need the first 3 test cases. So in this case, actually the first test case is kind of redundant. So we don't need this first test case. We can remove it. And that's about how we calculate MCDC. And an interesting fact about MCDC is that it is actually a very old criteria. And actually, an interesting fact is NASA requires 100% of MCDC coverage for any safety critical software component used. So although it is very old, we still learn it. So now let's come to an exercise to exercise what we have learned, to exercise all the coverage criteria we have learned today. So let's consider this function. This function is a search function. It is not implemented in the most optimal way, but it can show you how do we do all these kind of analysis. So this search function takes 3 parameters: a string, an integer n, which is the limit, and we can also a character to be searched. So what this search function will do is it will return the index of the character in the string unless it is not found. If it is not found, if the character is not found in the string, it will simply return -1. So this is a rough explanation of this control flow of this program, and we can see this is the control flow graph of this program. And in this control flow graph, we can see actually each one of the basic block is made up of one single statement, and it's actually quite straightforward. So can you tell me how many exit points are there in this control flow graph? We care about exit points because it's important. It could be very useful later on. So how many exit points? Since this function has a return, so we just need to count the number of returns. We have 4 exit points. Although they are not explicitly denoted in this control flow graph, we can still see that we just simply count the number of these returns. We can get 4 exit points for this control flow graph. And let's continue. So the first question is, how can we generate test cases to cover all statements? So how many test cases do we need here in this program? This is different from the single big while loop one, where we just need one test case to cover all. So how many test cases do we need to cover all the statements? 4, yes. Because that's why we need to count the number of exit points, because we want to reach from the start all the way to the exit. So this is one test case. This is the second one. This is the third one. This is the fifth. This is the first one. So 1, 2, 3, 4. So we need 4 test cases. And we can think about these 4 test cases one by one. So if we want to cover 1, 2, 3, what we need to do is we need to satisfy the first. We just need to satisfy one condition here to make the condition of basic block 2 to be true. And in this case, what we can have is this test case. So we just need to satisfy n equals to 1, and the first element, the first character of A equals to the character we want to search for, and this will return us 0. So which means that the character is found at the first byte of the string. And the second one is 1, 2, 4, 5. In this case, we need to also satisfy the condition of basic block 4, where n equals to 0. So we need to also we need to modify the test case so that it can satisfy n equals to 0, and this is what we get. And what about this one here? What about 1, 2, 4, 6, 7, 8, 9? What about this one? Can you think of a test case to satisfy this path? So the first one has to be true, it has to be false. The second one has to be false as well. So n can neither be 1 nor 0. Or n could be 0 but not 1, but then we won't satisfy this this condition here. So n has to be larger than 1 in this case. And then we have to satisfy, we have to find what inside the string of A here. So what we can get is n is larger than 1, and we can find the character inside the string here. So this is what we get for this path. And of course, the last one is the most complicated one. We have to we can't find the character inside the string, and n should be larger than 1. But we don't need to go through one iteration of the loop here. We just need to cover every statement, so we don't need to loop inside this while loop. So this is what we got. We can use this test case to cover the fourth situation. So we can use these 4 test cases to cover all the statements here. And now let's come to the branch coverage. So how many conditions are there in this? Wait, this is branch. Oh. How many conditions are there in this control flow graph? We can count it right now. 1, 2, 3, 4, 5, 6. We have 6 conditions. And how many decisions do we have here? 5, yes, 1 less, because these 2 makes up 1 decision. Sorry. And now let's consider the decision coverage. Let's skip the branch coverage, because branch coverage, what we just missed from the statement is only actually we are not missing. It's only this branch here. It's only this branch here. So what we need to do is we just need one more test case to cover based on this statement coverage test suite. So let's continue to decision to MCDC. So in order to achieve 100% of MCDC, we have to consider the table, the truth table, for each and every decision here. So let's first consider this first decision, where where we have 2 conditions, n equals to 1 and a0 equals to what? So can you imagine how this table will look like? How many test cases do we need here to achieve full MCDC for this decision? This is actually the same as A, B, and A and B. So this is A, this is B, and the condition is A and B. So we only need 3 test cases. We don't need the false one. It is kind of redundant. So as you can see, there are some explanations to explain why it satisfies MCDC, because in this table we can see that the decision takes the value of both true and false, and each condition here can take the value of both true and false. And we can also see that each condition is shown to be independently affecting the result of the decision. So this is why this table satisfies MCDC. However, we still have many more decisions in this control flow graph. So what we need to do is we need to go through the decisions one by one, and let's go through the second one. Oh wait, can you come up with some test cases, concrete test cases based on this MCDC table? So can you come up with a test case to make sure that both C1 and C2 are true? So this is actually quite easy. We just set n equals to 1, and the first character equals to the one we want to search for. And the second one, n equals to 1, and we will and the character is not on the first of the string. And the third one is n is not 1, but the character is on the first is the first character of the string. So in this case, this is actually a redundant case if we want to cover a branch, if we want to achieve a full branch coverage. This is if we do a full branch coverage, this we won't use this test case here, as you can see. So actually, if we want to do a full decision, compound condition testing coverage, it is the compound condition coverage actually subsumes the branch coverage. So however, if we want to achieve full MCDC, we have to consider all the decisions here. And now let's consider the second decision here, n equals to 0. And this one is actually very, very simple because we only have this decision only has one condition here. So we just take true and false for this branch, and we can achieve 100% of MCDC for this decision. And we also we need to go through all the rest of the decisions one by one in order to do MCDC. And that's all about today's lecture content. But don't leave now. We need to cover something about the assignment. I think you are more interested in the assignment. So let's see. Is it still available? So we haven't released. You cannot see this assignment yet. You cannot see it yet, but this is roughly what you will expect for your assignment 1. So in assignment 1, we will be doing some practical questions for. Oh, this is why we are not releasing it yet, and this is actually some code, and we have two big questions. The first one is about black box testing, where you will need to interact with a password validator black box. So this if you know some kind of pen testing, so you can get the source code of this easily. But I try to make it a true black box with some backend API, but there are some routing problems in the CSE servers. So in the end, I put it just in one HTML, but you just treat it as a black box. So in this black box, in the first target program, what we want to do is we want to test this password validator. And this password validator simulates how UNSW forces us to update our password. So when you update your password, you have to, UNSW forces people to update passwords from time to time. And when you update your password, you can't use the previous password you have used. So you have to, you can't use the previous password you have used. You can't have similar elements in your password with you can't have the same strings in both of your username and password, and there are many other restrictions. And you can get the descriptions of these requirements here from in the descriptions of the first question, and you will have to develop some test suites to test this program. And what you can do is you can access, later I will put this link in the specification, you can actually try out. The keyboard is not popping up for this internal computer. Oh, I can't type it. But you can try out your password as test cases here with this simple program. And the second question is about white box testing. where you will need to draw some control flow graphs using dot files, using the dot format, and you will have to develop test suites. And there are even some open-ended questions where you have to think about why sometimes white box testing would fail to reveal some failures or some bugs. So that's what you will be expecting for assignment 1, and you will need to submit. You will need to answer your questions in text files, and you can submit you can make submissions here in this web CMS, and you will have to do it before the end of next week. And this is because the consensus date of UNSW is the end of week 4. So if you don't like this course, if you don't like the assignments, you can drop it before you finish assignment 1. So this is quite fair, I think. So that's it for today's lecture. And if you have any questions, you can feel free to ask us, send us emails, or just put us right on the forum. Okay. This is not group work. This is individual. This one is individual. You have to do it individually, and you'd better not use large language models to help you to do these assignments, because nowadays it's really actually it's really hard to control large language models, the usage of large language models, especially with programming questions. But you can try, and I don't think it will directly give you the answer. You have to do it in the dot file format. It's very easy, the format. Yeah. I will send you some more references about how to draw graphs with dot files. Yeah.
So next week, what day?
Next week, Sunday, 10 p.m. Unless you are on an equitable learning plan, but I don't think any one of you here are physically attending this class is on that plan. So, okay. Next Sunday, 10 p.m.
The release.
Or release today, later.
Do you know what time?
Like before dinner, like in the evening. I will do it by afternoon.哎，好，拜拜。走。哇靠，它这个妈的这个不能用 laptop，这个太坑了。上次能用，对，它今天这个不知道为啥现在这个空调才开始发挥作用，我感觉。
哦，因为这个。
嗯。
我发现之前发现的那个
哪个呀？